Alrighty, so this is the final exam review, and I have done detailed reviews for all previous exams, so I will not go into too much detail of from chapter 1 to 5 because I have plenty of videos on my YouTube channel for you guys to go through. So chapter 1 to 7 will be covered. Final exam will have expect I cannot give you the exact number, so expect a number in between 12 to 14 problems. And yes, it will be heavy on chapter 6 and 7. So expect like 9 to 10 problems just from chapter 6 and 7. So those are the chapters you need to put all your energy in, 6 and 7. Okay? Now you will be given a calculator. So I don't recommend doing any math by hand, especially for this exam. Spend 5 minutes on Desmos, learn how to plug in equations. So I am not tech savvy. I did not get, when I did this course decades ago, I did not have a calculator. So I can solve math faster by hand than using a calculator, but I know it's so sophisticated now, the technology. You plug in your matrix A, and I'm telling you this for chapter 6 and 7. You plug in your matrix B, and whatever crazy big equation you give it, like something something, and you need this equation a lot in this course. And something something is just an example, okay? You just have to change A and B in Desmos, and it will calculate the exact result. So I highly recommend spend time on Desmos. It will save you a lot of time to review your work. And you guys are a lot younger, you can figure it out way faster than me. Now, the only other thing, like it's heavy on 6 and 7, but the only other technique that you should not miss at all is matrix multiplication. So don't just give up math skills completely. You must know how to multiply matrices by hand. Why? Because just like exam 1 and 2, if you saw a few questions where we had just for example, I won't spend too much time on it. For example, you're given some matrices here, okay, and some unknowns. This problem could be completely wrong, but I'm just giving an example. So for questions like this, you may need to like say we have an unknown here, okay? For questions like this, you cannot use a matrix. You cannot use Desmos. So you need to know how to multiply matrices to get the answer for questions like this, finding A, B, and C. So make sure you know that skill, spend some time. I have plenty of problems in the lecture notes, previous exam reviews, Edfinity. Make sure you solve that. And second, you must know how to find, like, parameterization is a skill. It will be used for every problem in 6 and 7, especially the kernel and the basis of a linear transformation type problems, which we'll discuss later on. Must know how to do parameterization. What it is, I have like detailed videos on my YouTube. So watch my YouTube videos. Okay, I have like plenty of videos in detail talking about a problem. So you should know how to go from a matrix in a row reduced form. Suppose this is a matrix, these are a bunch of variables. You should know how to go from here into picking your free variables, into like how many free variables, what are the parameters, stuff like that. So these are the only two things that I would say focus heavy from the previous section. Okay, rest depend on Desmos. Like, know everything about Desmos as your life depends on it for the final exam. Now we will begin with the most basic. Well, I think, okay, I'm sorry, I'm not very organized today. So we'll just begin from chapter 7, the topics that I think are more important, okay? So question must know, when they give you a linear transformation, must know what is a linear transformation and why it's a linear transformation. And if it's not linear, know why. So check if, say, L of X is a linear transformation or not. So suppose I give you a few options, okay? I give you number 1, My linear transformation is given by this vector 11, 7, 16. Okay. Number 2, my linear transformation is given by, say, this one. So 6x2. Now they're all different shapes and size, doesn't matter. 4x minus 4. Let's just say this is my third linear transformation is given by L of x. So the image of vector x. Now I'm not going to go into theory because I think you guys are reading the notes, watching the videos. I probably have a lot of videos discussing the basics of linear transformation, why it works, and how it works. So I will not go into theory, but who can tell me which of these three is a linear transformation? And if it is not, why not? And you don't need to do a lot of math. You can just look at it and check a very basic condition, and you should be able to hint. Let me should add a hint here. No need to do any math. Hint. No need to do any math. It's just observation. It's just observation.
Well, I would say guessing, but 1 is probably not a linear transformation.
Good guess. Why not? Okay,
Um,
good job. But why?
There's no difference. I don't know how to say it, but
the additivity.
yeah.
Okay. So no, yes. This will help, right? Good thing I picked this question. Why not? Because for a transformation to be linear, the zero vector, the zero vector with all the entries 0, must map to the zero vector in the image domain, like in the image part, right? If your 0 is not going to give you a 0 back, then the transformation is definitely not linear. And you're right, this is not linear because if I replace x, no matter what dimension, it could go from Rm to Rn, could be any dimension. This 0 could be only 2 entries, and the result could be like 7 entries. Doesn't matter. The 0 should go to 0. Okay, that's the basic condition for a transformation to be linear. So you can just look at it and you can say, oh, 0 is not giving 0, not a linear transformation.
So it's just a vector.
It's just a vector. Like 0 will give you 11, 7, 16, right? This is a fixed image. Every vector in your domain is mapping to 11, 7, 16, not linear. Okay. What about second? Who's going to guess?
I think x squared is not linear.
Yeah. Oh, second. Oh, this is not x squared. Did you mean this one?
Right. Sorry,
This
I haven't fully understand chapter 7 yet, but I've started it.
Okay, good. But x2 is usually, how we denote the variables, x1, x2, x3. So don't confuse that with the square, okay? But you're right, square is not fitting the definition of a linear. So clearly not linear, even though the 0 will match to 0 here, but it's not linear because it has a quadratic term. Quadratic term in the formula, in the closed formula. So two conditions, right? Should not have a quadratic term. 0 should map to a 0. That fits for question number 2. Well, I probably have picked the wrong example and it might not be linear when I do the definition, but this is linear, okay? Yes, linear. Because 0 is going to 0 and I don't see a quadratic term. So in exam, we will, if you see a question like this, do not spend too much time, but definitely check for squares, cubics, square roots. It should be a linear combination or a scalar multiple is fine, but 0 should map to 0. Okay, this is good with everybody?
Yes.
Okay, now we know that what is a linear, when a transformation is linear or not. let's talk about vectors basis. So I don't think we ever discussed the size, norm, or some other things, right? And you will see a question like this. So if I give you a vector 2, 1, 1, is everybody able to find this for me? This is called the norm or length. So whatever word you get based on your major, you should be able to figure out that when I say norm of V1 or length of V1, this is what I'm talking about, right? So 2 square plus the square of each entries. So 4 plus 1 plus 1 is 6. This is okay with everybody, right?
Yeah, this one is pretty straightforward.
Pretty straightforward, just the background information, because we will need this a lot, and like expect a heavy expensive question on Gram-Schmidt. Okay, I can never pronounce the spelling of it right. We will not even embarrass myself here. Okay, question. So definitely you will get a question. Expect one in exam. So make sure you are a pro with Desmos and can solve this, plug this values in Desmos and get the answer. Expect one in exam. So in in-person courses, we don't do this because now calculators can. It's like a process, right? You plug in 3 vectors. The calculators are so sophisticated. You give them a vector of size 100 million entries, they will still give you an output in like 2 seconds. So I think it's a waste to learn, but I guess we are still keeping it in the online curriculum. So we have to learn. But good news is you're not wasting any time. You're just plugging in entries in Desmos. But you must remember the formula, which is, I know I hate remembering formulas, but this is what we wanna do when you get a question like this in exam. So you'll be given a set of or a basis for a vector space. Usually we'll have 3 vectors because anything more than 3 is just gonna be too much work. So I have to find the Gram-Schmidt normalization for this. What is the first step? You probably have done a lot of problems on this already. So we pick our first vector V1 in my orthogonal basis will be the same vector as X. I pick that as the same vector, and these are the only steps that you have to memorize. That the first step, the first vector in your basis is going to be the same as given to you. The second vector in your basis will be the second vector in your given set minus the dot product of the second vector with the V1 and the dot product of V1 by itself. And just this will turn out to be a scalar. Oh, I should have done one more background here. Okay, this formula is what you have to memorize, and finding dot products of vectors are really straightforward. Let's just do a quick recap here. So suppose I want to find the dot product of y and v1. Y is 1, 3, 1, and I'm finding the dot product with v1, which is 2, 1, 1. How do I do it? It should give me a number back. Multiply the corresponding entries. What do you get? 6. This makes sense to everybody? Negative. So I've got 6. And what is the dot product of v1 with itself? So it's basically the norm squared. So 4, 5, 6. 6, and then I copy the vector back, 2, 1, 1. So each v2 should be a vector. v1 will multiply by a scalar, and that's it. It's really free points if you can remember these formulas. And what do you get? Once the final answer is, this is just 1, so I've got negative 1, 2, 0. And then, because I have 3 vectors in my original basis, I should have a v3 also in my, and no need to go through any theory for this. They're not useful for your exam. We are focused on getting the highest grade possible, and that's what we are doing here. So this is the formula. We do the same step. but for the last vector, and we have to consider the v2 here. So I'm going to do z times v2, 2 dot v2 times this. And that's the formula that you have to remember. If the chain keeps going, don't ask me why, because it's not useful for you guys. If you had more vectors, you would just keep subtracting. And when you do this math, you can check your answers. The answer for this one would be negative 17 over 30, 17 over 6, and this is it. This is Gram-Schmidt. You will get a question like this with 3 vectors. Probably it will not be 3 components. More than that, it will have 4 or 5 components, but you have access to Desmos. So just remember the formulas. Focus on what I need to do for a question. The whole point of this exam is you must remember the first 2 steps of that problem. After that, things will fall into place and you'll start to remember. But the first 2 steps, no matter what problem I give you, you should know by heart. If I give you orthonormal basis, you should know, okay, this is the first step I have to do. Second step. And then after that, things start falling into places. So this is Gram-Schmidt, which is very important for your exam. Now, the second important question that you definitely should expect is, where was it? Is the orthogonal basis. Wait. Hold on. Yeah, this one. So question, and all these questions are like, if I'm talking about this in the final review, expect one in exam. So the question will be, find a basis for the orthogonal complement. And you have seen this in the math 242 in-person reviews. It's everywhere. It has been asked in every final exam. Orthogonal complement. Orthogonal complement is of W, where given the spanning set is, the basis for W is 5, 15, 3, 10, and then I have 3, 9, 2, 5. So I'm given the basis of W, and I want to find the basis of the orthogonal complement, which is denoted by W with a upside down T, the perpendicular sign. This upside down T means the orthogonal complement sign. Now there are 3 simple steps to follow, but I want you to remember 2 things so that you know that your answer is correct. Look, what is the vector space we are talking about in this question? I know I have a subspace. I'm the spanning set has 2 vectors, but which vector space am I in?
R4?
R4. Good job, because you have 4 components, right? R4. And what is the dimension of R4?
4.
4 directions, 4. Yeah, you even know the standard basis of it. The 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, right? That's the standard basis, and we'll get to it later. Keep this in mind. This is the standard basis. It has 4 dimension. I have 2 vectors in my basis of W. That gives you your first hint. I should have 2 vectors. I should have 4 minus 2 vectors in my orthogonal complement. That's what it tells you right away. If you have 3 or if you have 1, you made a mistake somewhere. So immediately know this information just by looking at the question, and then we follow the simple steps to find the basis for orthogonal complement. Okay, solution. Okay, I combine the vectors in my original basis of W, which were 5, 15. I augment them in a matrix, 3, 10, 3, 9, 2, 5. I do the transpose, and I've got 5, 15. Everybody knows what transpose means, right? Or you should know now, by now at least. This, and then I find the RREF. And you can plug this in your Desmos thing, easy peasy. And the RREF, when I did it, it was 3 over 5, 2, 0, 0, 1 over 5, -1, and I just gonna augment it with zeros just so that setting up the equations is a little easy when we are doing the parameterization. Now remember I talked about parameterization and how many free variables and why free variables. That's the key because you'll use it everywhere. So in this case, I have like 1, 2, 3, 4. I have 4 variables and I have only 2 non-zero rows. I have 4 variables and 2 non-zero rows in my RREF. It's not enough, so I should have 2 free variables, right? So the number of free variables is 4 minus 2. So and then if you know how to find the free variables, x1 cannot be free because it has a pivot. I go down. This cannot be free because this has a pivot. So clearly x2 is free. Let's call that guy a t. And x4 is free. Let's call that s. Right? And because you need 2 free variables, just like the eigenvalue problem, right? You need 2 free variables because you need 2 vectors in your orthogonal complement, which we checked right here. So it makes sense. So far, I am following the track. I have 2 free variables. It looks promising that I'll have 2 vectors in my basis. So let's rewrite the solution set. So I have x1 equals -3x2 I guess I could multiply it by 5. -3 over 5 x3, and I got -2 x4, and then I have x2 is t, x3 is, so I have 1 over 5 x3 equals x4, right? So what does that tell me? x3 is 5x4. So my goal here is to write everything in terms of the parameters. So this will give me -3t, -3s, and -2s. I'm just replacing every variable with the parameters because the final answer should be in terms of the parameters. So what do I get? Any questions so far?
Doctor, I do have a question, which I feel maybe I should have understand, but 1 over 5 is a pivot
Wait,
on
which
the
one?
on the RREF. I ran into a problem with that. 1 over 5 is a pivot
It's a pivot. Yeah, you could multiply it by 5
and get a 1.
and get a 1. I didn't, but you would
Okay.
get the same answer afterwards. Yes.
But that's something we should see. We don't have to go and we don't have to do it. We should be able to see 1 over 5 is going to easily be a 1.
Yes, because you can multiply the whole row by 5. So when you do it in Desmos, it will not give you 1 over 5. It will give you 1 and the entry
Okay.
above it as a 0. But because I did it by hand when I was doing it on paper, I just left it, being lazy.
Yeah, when I did the REF for it, the bottom row was 0, 0, 1, -5.
Yes, it should be that. Yeah, but Desmos will give you the right answer. But you see the end goal, right? We
Yeah.
are eventually gonna parameterize it. So
Right.
whatever gives you the correct answer is, so this is another thing where I say that parameterization is important because you need to pick the right free variables and the right pivots. But we can like get around a little number game, right? We can have a fraction and still end up with the correct answer because now you're so far into the course. Will not be very hard on about the positive. There should be a 1 there. There should be a 0 above. I mean, you get it, right?
Yes, I did notice one time I didn't do it all the way, but when I parameterized both ways, I was getting the same answer.
Yeah, you
even
get
with-
the same answer. Eventually, you end up with the same parameters, you get the same answer. So let's write down the answer here now. So I've got x1, x2, x3, x4, which equal to x1 was 3s minus 5t, x2 was t, x3 is 5s, and x4 was s. Wait, did I make any changes here?
I think that's right.
Okay, and then I think you guys are champions in what to do here. Just break up your two vectors, and there you go. And then you have a t common, and then it becomes -5, 1, 0, 0. And you see, I had two free variables. That gives me two vectors in my orthogonal complement basis. And that's it. If you get a question like this in exam, which I promise you will, you combine your vectors, transpose it, find the RREF, parameterize, and just have this little background in your mind somewhere that, okay, I have R4, you could have R5 in exam, and then just make sure that you have the right number of vectors in your orthogonal complement to verify your answer right there. And so the basis of the orthogonal complement will be these two vectors. And Edfinity does a good job to tell you during exams in each question how to plug in your answer. And when I go through your work, if you have the right math on your paper, but you just did something wrong plugging in your answer, I do give you the points. So I would not worry about it too much. Okay, this question is very important. You'll get it in exam, and everybody can solve it, right?
I think so.
Okay, good. Now there is another question which might be phrased differently in exam. It's called the finding the closest vector, or in this case, sometimes it might be called find the orthogonal projection. So I have a question. The formula is the same. Find the orthogonal projection of, say, this vector, -17, 36, -11, 20, into, and you'll be given a subspace, into the subspace. And you'll be given a subspace which is -2, 4, 3, 2, the basis of it, and then second vector is -4, -3, -1, -2. So why I say this exam is going to be heavy on Desmos, because everything is based on a formula or RDF. So if you remember the formula, find the what is the normal equation, how do I find the closest vector, it's all in my lecture notes also. Just make sure you can solve every problem here. If you go to chapter 6, these are the lecture notes. Every single formula, every problem that you can possibly get in exam has been solved here, except Gram-Schmidt, but we already discussed that, right? So if you can solve every problem in these notes, I have probably explained it. There might be a video somewhere also on YouTube for difficult topics, but I would just go through this. Now, how do I find the orthogonal projection of a vector? Let's call the vector B, that's the standard notation. The vector B for which I'm looking for the orthogonal projection, and the subspace. So I construct my matrix A by augmented the vectors in my basis of the subspace in question. In this case, it's 2, 4, this. -4, -3, -1, -2. And to find the orthogonal projection, in other words, the closest vector to be in this subspace, which is denoted by the vector P, you have to memorize this formula. I can never memorize it, but I know how to derive it, which we will not get into. But this is and this is what I was talking about. If you define your matrix A and B in Desmos, you can just keep this equation there and just keep changing it and get the answer. So please don't ask me how to plug this in Desmos, but I highly recommend you practice with this. And that's it. So all these problems are really technical. That should be the answer when you plug it in, just for reference. I mean, you have to memorize this formula. As soon as you show your scratch paper to the camera before final exam, write down a few important formulas, like this one, on your paper somewhere, so you don't forget it later on. Now, this is finding the closest vector or finding the orthogonal projection of a vector B onto a subspace. This is what we do. And then there is another application in chapter 6, which is the least squares approximation, which is the best part of linear transformation, right? How to find the best fit polynomial. This is important. And the second thing that you definitely should expect in exam is finding the best fit polynomial or best fit parabola or something, okay? Best fit polynomial. And again, the same formula will be used later. Polynomial, using least squares approximation. Using least squares. Okay, so how do we go about this? So in every question in exam, you will be given a polynomial, parabola, log equation, whatever curve, power curve they want you to fit the data value in. In this case, my polynomial is y equals ax squared plus bx plus c. Okay, and my data set is, I have to fit these points, 0, 2, 1, 4, 3, 5, 4, 6. Okay, I want to find an equation of a quadratic polynomial that best fit my data set. This will be a typical question in exam, and expect one in exam. Now, ultimately, you will end up with finding some vector A, some matrix A, some vector B, and this is the formula that you'll apply later on. But how do I get to that matrix is the bigger problem, right? And that's what I want you to practice. Just make sure you can construct the first few steps for these problems. Now, what we do here is this is a course about linear equations, and I need a set of linear equations. How do I get a set of linear equations? I plug these data points into my parabola one by one. So that's the first thing. Think of it like this. So I'm plugging in point 1. This is the x value. This is the y value, right? So when y is 2 and x is 0, my first equation is this. So 2 equals 0a plus 0b plus c, right? And then I plug in the second point. So plug in y equals 4 and plug in 1 in place of x. So it will just be a times 1 squared, b times 1 plus c. Do the same thing for the third equation, which will give me 9a plus 3b plus c. Then I do the same thing for the last equation. I'll have 16a because I'm plugging 4 in place of x. All good here so far? 4b plus c. So you see, now it looks like I'm in the linear algebra course again because I have a system of linear equations. And now I can begin finding my A, finding my B, and it all becomes the same formula, plugging in Desmos. Does this make sense to everybody? This is the step that everybody gets blank in during exam, and then they just don't know what to do. That's what you're supposed to do. Get a set of equations from your data points using the given curve. Now, so my matrix A will
Dr.
be,
Joshi,
yeah, question?
I was just going through the videos for this section, and he said plug in, you know, the ABC into Desmos. Will it accept ABC as a vector?
ABC in Desmos, but that won't take you anywhere.
Right. I mean, that's what he's, well, I think he was using a different matrix calculator that maybe the TI, but it accepts,
Oh,
he
you
said,
are not allowed that. So ignore him.
No.
Ignore whatever he. See, the videos are usually sometimes are meant for the in-person students, right? We allow them some
Right.
matrix calculator, but you are not.
So Desmos definitely will not accept the letters, right? It doesn't. I'm pretty sure that's what it.
It
I was
won't
like,
accept. It won't take letters. No.
right.
That's
Okay.
why, you know, that was my first disclaimer. Like, you can
Right.
depend on Desmos for this exam, but not for problems like this. So
Okay.
you need to know how to multiply matrices, because Desmos won't give you the answer.
Right. He punched it in, and I was like, wait a minute, we can't do that on Desmos. So I figured we're gonna have to do it by hand.
No, or you could do this, right? You could find the system of linear equations, because that's the general route how we do it. For any courses, you need a system of linear equations, and then you have to apply the least squares formula for this.
Okay.
But is this process clear to you, that you plug in the data points into your quadratic, you have a
Right.
system
Yes.
of linear equations? Okay, and then you construct your matrix A, which are basically the coefficients of the variable A, and then the second column is the coefficient of variable B, and the third is just 1, right? And then the vector, the B, will be the right hand side. So 2, 4, 5, 6, right? And the vector X is basically, you're looking for ABC, the end goal. So the 2 steps I want you to know for every question in least squares. What are we looking for? We're looking for coefficients A, B, and C. So I have a nice polynomial that fits my data set, right? So I'm looking for X, which should be a 3x1 vector. That's another hint when you plug in the matrices in your Desmos thing. And I need to construct a matrix A and B so that it works. Now, the formula I already gave you to find the vector X. Now, we're not normalizing it. So the formula is A transpose A inverse A transpose times B. And you have everything. You have A, you have B. Define A and B in your calculator and solve this. You will end up with a bunch of with 3 entries for ABC.
So it'll give us a column vector, and that is ABC.
That is ABC. Now, okay, I did not do this, okay, because it was too much math for me. So if anybody can do it fast, this is practice for you guys, right? If you have the answer, let me know. I'm just going to leave it as alpha, beta, gamma. So whatever numbers you get at the end, your polynomial will be that. Alpha x squared plus beta x plus gamma. So what happens in exam, they ask you to find the polynomial at the end, right? The polynomial is this with numbers here. That should be the answer on affinity when you plug it in. But of course, I'll give you partial credit, but you must show something. Now, I know you have a calculator, but at least write down the equation somewhere on the paper so I can read, right? And I know what you're doing. Or write down the system, like okay, I find my A, I find my B. Then it's very common that you screwed up calculation in finding A and B and you got the wrong answer. But at least you had the process going on in paper. So show that on your scratch paper to get some partial credit, okay? Now, the second thing about this one, where we say finding the matrix. Anybody, any doubts? I think this is it from chapter 6. I don't have anything else. Chapter 7 is linear transformation now. So we're going to start from 7.1, which is finding the matrix of a linear transformation. Now, I have a video on YouTube where I discuss in detail about this. YouTube on chapter 7 or 7.1 for that matter. The concept comes into play is the standard basis and the ordered basis. For example, if I give you a linear transformation, so L is a linear transformation. This is the question. And I'm giving you the image of random vectors. I'm giving the image of an ordered basis, not the standard basis. So this is -3, -3, 1, -11 is mapped to 10, 29. And then I have the linear transformation is taking -7, -4, and 6 to say 31, 42. And then I have the linear transformation taking 4 to -3 to -17 and -25. I want to find the matrix. Find the matrix A of linear transformation L. Now, I have a detailed videos on YouTube. What is a matrix of a linear transformation? What it does. This is my favorite topic in this course. And you can read through more in my lecture notes also. But in this review, we don't have too much time. So we'll focus on how to solve this problem. And why can't I just make a, well, first thing first, tell me what is my domain and what is my range here? So, my linear transformation is picking a vector from some vector space and throwing it into another vector space, right? That's the whole point. That's why it's used in game theory. But where is it picking vectors from? If you see, my linear transformation is taking a vector of size 3, right? So my vector space of the domain is R3, and it's taking this vector -3, 1, -11, and is throwing it in a vector space R2, right? Because there are only two components now. And that's the good part. So my linear transformation maps a vector in R3 to R2. So the matrix of the linear transformation should be of the size, anyone? Okay, this is the size of the matrix. Like, just know that. Because my linear transformation is going from R3 to R2. Is this clear when I talk like this, that it's taking a vector from R3 and it's giving me a vector in R2? Do we understand that part?
Yeah.
And that's your hint. So if my linear transformation is going from here to here, my matrix for that particular linear transformation should be of size 2 by 3. Just reverse the order. Now, the bigger part is, because it's not taking the standard vectors in R3, if it was taking the standard vectors, you know what would happen? If my linear transformation was like this, it would give me some vector, we don't care, and it was taking 0, 1, 0 to say -11, 10, and it was taking L 0, 0, 1 to say something 9 or 8, then my life would have been so much easier, because I would have the standard basis and their image, and my matrix in that case would just be 7, 12, -11, 10, 9, 8. Easy peasy. And I have examples in my lecture notes doing that. So why is this question difficult? This question is not that simple, right? You cannot just copy these vectors and make it a matrix. Don't do that in exam. This question is supposed to be difficult, because you're not taking your standard vectors. It's not taking your standard basis. So you have to recall the concept called change of basis matrix from chapter 4. Change of basis matrix from chapter 4. And that's the concept we use here. We don't need to go into too much detail. Now, who's going to tell me what's the formula?
I think we have to multiply
By the inverse.
by the inverse of A. Well,
Exactly.
the inverse of the R3.
Exactly. So the basis of this linear transformation, which should be 2 by 3, just for reference to check your answer, you will write down the resultant the ordered basis that you're getting as a result, but be careful, you have to multiply by the inverse, because that's what we do to get the standard basis, right? And this was 6, and this was 4, 2, -3 inverse. And that's it. Once you do this math, multiply this, this can be done in Desmos. That will be your basis. That will be your matrix of the linear transformation. 8, 8, 7, 3. And you know what this matrix means? That I can find the image of any vector in that domain by multiplying it by this matrix and get the image. So it's basically a formula, but just more twisted and more complex now, because they're not dealing with the standard basis anymore. But you will get a question like this in exam. So make sure, just know that this should be the final answer. The final answer should be of 2 by 3 size. That will reduce a lot of errors that I've seen in the past. Wait. Okay. Now, the second thing, actually now the most important thing that you'll see in exam is, well, let me write down some important points from 7.2 here. So things you must remember by heart. Things, facts to remember before we go into the final exam. Okay, and you have plenty of days left. Even if you spend like 2 days per chapter, you should be good. Number 1, the kernel of any linear transformation is nothing but the null space of its matrix A. Null space of A, where A is the matrix of that linear transformation. Okay, and we are champions in finding null space. I have detailed videos on YouTube how to find null space. We did discuss this in the last exam, so we will not go there. But remember, kernel means null space. And the range of a linear transformation is nothing but the column space of that matrix. Column space of A. Okay, now, third thing, they will ask you in exam if a linear transformation is injective or one-to-one. A linear transformation is injective or one-to-one if and only if the kernel or the null space of that A only has 0 vectors. Okay, what does it mean? Just like injective one-to-one functions, the only vector that is giving me all zeros is the 0 vector. That's what it means. No other vector maps to the 0 vector except the 0 vector. So we will, this is not a theory class, but remember this, okay, for the exam. For this, a linear transformation is just for, fill in the blanks problems, onto surjective, same word, same meaning, different words. If and only if the dimension of the null space and the column space equals the rank of A. So the dimension of the range, in other words, dimension of the column space equals to the rank of A. Okay, which is equal to the dimension of codomain. Now you'll ask, what is the codomain? Just like the previous example, let me just, and now I will post these notes for everybody. But you see this one, this linear transformation in the previous example, it was taking R3 to R2. R3 was the domain, and the dimension of the domain is 3. R2 was the codomain, and the dimension in this case is 2. Okay, that's what they're looking for. So just remember that. And if these things match, then the linear transformation is surjective. Now, I don't know if you're getting a question of fixed points. Okay, sorry, let me just stop share for a minute. I don't want to go into this topic if we're not going to do this in the exam. Hold on. Sorry, I'm almost done here. I'll just give you information that you need, nothing more. Okay. That's it then. We find the kernel basis and we find the image basis, and this is all we need. Actually, we don't even need the injective part. Okay, let's do a question so that we know how to solve a problem, because we will get a problem in exam. So, do I have a question that I can solve in front of you guys? I guess I don't. Okay. That sucks. But we know how to calculate. Let's just pick the same example above. Okay. Suppose I gave you the matrix of the linear transformation. Okay, let's just do a problem. We can make up a problem here. So we have question, find the basis for kernel and image, which in other word is called the range of the linear transformation. Okay. Now we will L with the matrix A. Now, why am I not too worried about this? Because it's basically finding the null space and column space, which you guys know how to find. It's just different terminologies. And I probably have a video on YouTube explaining this in detail and why it's called the kernel, why it's called the image, how it works, all detail if you're more interested in. But suppose I give you a linear transformation, or I give you the matrix of a linear transformation, which is, for this question, we'll pick 2, -1, 4, 1, 5, -2, and 0, 3, 1. Okay? And I wanna find the kernel. What is the kernel of a linear transformation? Kernel is basically what? Null space of A. And who will tell me how to find the null space? Because you already did an exam on it, right? You will find the RREF of A, and then you would find the free variables and introduce parameters and rewrite your x1, x2, x3 in terms of parameters, and that gives you null space. And how do you give me the image of the range? So 2 words they can use in exam: image or range of the linear transformation, right? Basis of image or range, which is basically nothing but column space. And I think I've drilled you guys enough on the null space and column space basis. And once you have the RREF, you should be getting to this basis in no time. Now, this is one thing. Now, I just want to talk about one more question that you may expect in exam, which is, how do we go from an orthogonal basis to an orthonormal basis? So suppose I give you a set of vectors, let's just call it, let's pick my vectors this, okay? I have a basis of a subspace given by these three vectors. Okay, these are not orthogonal. Well, first of all, how do you check if a set of bases is orthogonal? Who's gonna tell me? V1, V2, V3.
Check the dot products.
Good job. Check if the basis is orthogonal. All of the dot products, right? Orthogonal. So what you check is you do v1 dot v2, you do v1 dot v3, and you do v2 dot v3. And if they're all 0, then yes, it's orthogonal. It's orthogonal. If they're not 0, then it's no. In this case, I can tell without even checking that they're not orthogonal, right? But suppose they were, and so you won't have to check because the exam will already say that, okay, this is an orthogonal basis. How do you find me an orthonormal? And don't do the Gram-Schmidt. That's too much work. Orthonormal. Orthonormal basis. It's really one step. What you do is you take the same vector, but normalize it. So just divide it by its length, and it becomes, because we already know they're orthogonal, we just normalize it and it becomes orthonormal. Just something to keep in mind if you come across it during exam. And I think this is it. These are all the, like, exam will be heavy on chapter 6 and 7. So this is all that you have to worry about from chapter 6 or 7. Definitely spend some time because you have plenty of time. Oops, sorry, my bad. You have plenty of time to go through the lecture notes, right? Definitely go through the lecture notes and do all problems on affinity. And this is it. If anybody has any questions, any topic that you're struggling with, let me know, else I'll let you go.
Doctor, can we look at that? I don't know, it's towards the end where you did the change of basis matrix.
Change of basis matrix. Oh, here.
So that was,
Yeah.
like CB inverse. That's
yes. So this, have you been to my YouTube channel?
I have. I've watched it. Yes.
Yeah. So there is we are looking. This is the vector space I'm picking the vectors in, and this is the vector space I'm throwing my vectors, right? That's what is happening. But the image you get is in this vector space, R2. So I need to do a change of basis in R2.
So we want the inverse of the R3 matrix. Yes.
Because I already have the image of the vectors in terms of R3. There is a whole derivation for that. Why am I multiplying it by the inverse of this vector, this ordered basis? But I have explained this in detail, why it works. And yes, it uses the change of basis, C times B inverse in this case. Somebody asked me in the last review also, why do we multiply by this on this side? So, and I had an answer for them, like, because it's this and it's this. It has to do with this, right? I'm getting my image in this basis, but I want the image in terms of the standard vectors. So I have to multiply by some inverse from that side. But
so you multiply the side times B inverse.
Yes. So this is also, you can remember this formula by this. You take the ordered basis of the image of vectors in the domain. So domain is R3 in this case, right? And that's why I took the inverse of that. So whenever you calculate your linear transformation, the matrix of a linear transformation, take the vectors in the domain and inverse those vectors. and then multiply by the image of the vectors in the codomain. Make sense?
Okay. Yes, that helps.
But
Thank
you
you.
will know why we have this order in the video, but it's like a process. Okay, make sense? Sorry, let me plug in my laptop. Anybody, any other question? Did I answer your question?
Yes, the way you explained it right there helps me understand it. I'm gonna have to review that whole section. Thank you. I want to watch your video again.
Yes, and the lecture notes too, because I write a lot of language in the lecture notes. The good thing is, and this was a suggestion by a former student who were like, okay, can you post your blank notes so that I can test myself? If I have memorized all the definitions, theorems, process, I can solve the examples on my own. And I was like, sure. And I liked her idea. So I was like, I post my blank notes too. So the students can go through the filled notes and then try to fill it in themselves. And then you are sure that you know all the theory. But yeah, any other question? Alrighty. Well, guys, I wish you all the best for the final exam. You have been a wonderful bunch, and I hope you'll all do great in the final.
Thank you, Doctor. I would say
Thank
that
you.
this is the first experience I've had with a professor engaging directly since I've been doing online like this. So I thank you for your help.
Oh no, well, I'm happy that you are enjoying this course. I'm sad that nobody else is doing live meetings. Well, I'm glad you enjoyed, and yeah, let me know if you want to book a one-on-one. If you have a doubt, I'm always happy and available. Just send me an email. Alrighty, so I'll let you guys go, and good luck.
Thank you.
Yeah, no worries. Thank you, Jake. Bye.